In this class, we will solve some examples on 2's complement signed numbers. So I have taken 3 examples, very simple examples. We will solve these examples. So let's get started with the first one. It is 6 minus 2. So one of the very important point that you need to keep in mind is computer will always do additions. It will not do subtractions. So why? The reason behind this, you'll be able to understand this in your next semester courses like digital logic design and computer architecture. So there you will get a complete idea why the computer will do only additions, not subtractions. So the subtractions are also done by these additions. So this is how the computer will interpret this mathematical equation, which is 6 minus 2 is interpreted by the computer as 6 plus minus 2. Okay, so now, this calculation has to be done by the computer. So how it is going to do? The binary equivalent of 6, as you know, it is 0, 1, 1, 0. So this is the binary equivalent of 6. And what about minus 2? How the negative numbers are represented by 2's complement method? Just take the magnitude. It is the plus 2 is identified as 0, 0, 1, 0. On this, we have to perform 2's complement. This is what we have learned in our previous classes, right? So the 2's complement, if you apply 2's complement on this, we are going to get 1, 1, 1, 0. So the next step is to add 6 with this negative number representation of minus 2. 1, 1, 1, 0 has to be added with 0, 1, 1, 0. So if you add both of them, the result is going to be, so this is what the result that we are going to get. Here we have a carry. So 1, 0, 1, 0, 0. So this carry will get cancelled. So no need to, this carry will be cancelled. And the decimal equivalent of this is 4. Whereas 6 minus 2 is 4. So this is how the computer will do the calculations on the signed numbers. So coming to our next example, it is 3 minus 5. So we know that this is going to produce a negative number as the result. So how it is going to interpret? First we will understand that. It is 3 plus minus 5. So here the binary equivalent, because this is a positive number, the binary equivalent of 3 is 0, 0, 1, 1. Now minus 5 is a negative number. How it will convert? As you know, the 2's complement method. So the magnitude and 1's complement we are going to do on the magnitude of this 5, and to this 1's complement if you add 1, which is a 2's complement method, we are going to get the representation of minus 5 as 1, 0, 1, 1. Now if you add 3 plus minus 5, the result is going to be 1, 1, 1, 0. As you know, we are getting, so as the leftmost bit is 1, so what it represents? So we are expecting it to be 3 minus 5 has to be minus 2. Now because the leftmost bit is 1, it is a negative number. So how can you get the magnitude of that negative number? So it is the binary value of minus 2, right? So how can we get that is apply the 2's complement on it. You are going to get the actual magnitude of the number. So if we apply 2's complement on it, first 1's complement 0, 0, 0, 1. If you add 1 to it, it is going to be 0, 0, 1, 0. And because we have converted this negative number and we have applied this sign to this magnitude, which is going to be minus 2. So the result of 3 minus 5 is minus 2. And coming to our third example, so if you take this, it is a very straightforward addition without sign numbers. So the what they have given is 2 minus minus 3. So 2 minus minus 3, both of them will get cancelled and it will become plus. So which is 2 plus 3. If you add, both of them are positive numbers. If you add 2 plus 3, it is going to be 5 and the result is going to be 5. Okay. So this is how the negative numbers, this is how the calculations on the negative numbers and the negative numbers are represented by using 2's complement method. So that's it for this class. In the next class, we will understand another very important concept, which is range of numbers possible with a given number of bits. So we will understand that in our next class. See you in the next class.